The goal of this course is to give you a high-level view of life cycle assessment, LCA, so that you understand its value for making more sustainable choices. We will look at what an LCA is actually measuring, what the results might tell you, and why you would want to do one. Throughout this course, we will use several hypothetical building examples. Let's start with asking what LCA is and what it can tell you. Please click Next to get started. Humankind benefits from a multitude of resources and processes supplied by Earth. Collectively, these benefits are known as ecosystem services and include products like clean drinking water, minerals, metals, as well as processes we depend on, such as the decomposition of waste, nutrient cycles, and crop pollination. As human populations have grown, so have the resource demands imposed on ecosystems and the impacts of our global footprint. And as environmental impacts of human activities become more apparent, people have turned to the LCA methodology to help them measure the possible impacts of their actions. Click the History of LCA button to read how LCA has developed over the last 50 years, and read the on-screen text to learn more about ecosystem services. You can also download a copy of the United Nations Millennium Ecosystem Report by clicking the resource icon above. Every product connects to Earth and Earth's ecosystem services. If we consider a building, there are millions of products and services that go into its creation and use. For example, windows, wiring, heating, and cooling systems are needed. At the end of the building's life, even more resources are required to dispose, reuse, and recycle all these components. At every step in a building's life, there are connections with Earth, and it is these connections that an LCA measures and evaluates in terms of potential impacts, cradle to grave. To help define these connections, value chain maps are created. Read the on-screen text and then click Next to learn how you would start mapping the value chain of a hypothetical window. Mapping a value chain involves looking at both the upstream and downstream activities in a product or service's life. If we were mapping the value chain of a window, the upstream activities would include the manufacturing, the transport of raw materials to the manufacturing facility, and the raw materials needed to make the window, such as the wood, aluminum, and glass shown on screen. Downstream activities would include the distribution and the use and final transport to end-of-life activities, such as recycling or landfill. Depending on the goal of your LCA study, you might map the supply chain of your raw materials as well. Click on the wood to view its supply chain. Wood for windows typically comes from pine trees that must be harvested, debarked, and milled. The milling operation provides the lumber as well as the co-products of wood chips and sawdust. Now let's go back to the trees and think about what it takes to grow a tree. We need soil and we need water. Both are natural resources from Earth's ecosystems. We also need carbon dioxide from the air, another natural resource. Let's move to the harvesting operation. Here, things get more complicated. We need diesel to operate the truck and oil for the saws. When we combust the diesel, there are direct emissions to the air. Similarly, when we move to the debarking and milling operation, we have more direct air emissions, and we likely need electricity to run the equipment in the plant. Now this electricity has its own supply chain, and if we dig back through it, as well as the oils and the diesels, we again find direct links to Earth. So you can see how the mapping process ultimately leads us to all the connections with Earth that our product has. Read the on-screen text and then click Next to learn how these connections, the elementary flows, are inventoried in what is called life cycle inventory data. In an LCA, the connections with Earth are measured as elementary flows. These are resources drawn directly from the air, soil, or water without previous human transformation, or they are emissions released into the environment without subsequent human transformation. In an LCA, it is not how many kilowatt hours of electricity you use that matters, but rather the elementary flows required to make that electricity. The elementary flows will change if we make the electricity with coal or gas or solar or wind. The final output of our value chain mapping is an inventory of elementary flows. Click on the Elementary Flow button to see a hypothetical list of what could be included in the life cycle inventory of a study. Then click Next to learn how the life cycle inventory is evaluated with an impact assessment method. So now that we have life cycle inventory, how do we calculate the potential environmental impacts of this inventory? How might the emissions of 1 milligram of benzene affect our ecosystems, or the use of a kilogram of copper, or a gallon of water? Here is where the next step of an LCA comes into play, the calculation of impact assessment. In this step, the quantity of an emission, such as benzene, or a resource extraction, such as water, in the inventory is multiplied by a factor that measures the potential for some impact to occur. There are lots of potential impacts that can be measured in an LCA. Click Next to learn more. There are many different LCA metrics, impact categories, that can be measured in an LCA. On the x-axis of the graph on screen, you can see 13 common impact categories that were measured in this hypothetical window study. The percent each activity in the value chain contributes to the total impacts in each impact category is shown on the y-axis. If you would like to read more about commonly used LCA metrics, please click the resource link. To learn more about the science behind the factors used to calculate these metrics, click the example icon. To move on to why you might want to do an LCA, click the Next button. Let's look at the global warming potential impact category and how this category is calculated. If you look at the picture on the right, you can see in red the heat that the Earth is absorbing from the sunlight. This heat is reflected back into the atmosphere as infrared radiation, where the dominant gases, nitrogen and oxygen, are transparent to infrared. However, the so-called greenhouse gases absorb some of the infrared radiation. They collect this heat energy and hold it in the atmosphere, delaying its passage out into space. A gas's potential in relation to CO2 to absorb infrared radiation is reflected in the factors you see listed on the left. So carbon dioxide, CO2, is the baseline with a factor of 1. Methane is 25% more potent, and nitrous oxide 298 times more potent at absorbing infrared radiation than carbon dioxide, CO2. By multiplying the quantity of each greenhouse gas emission in the life cycle inventory by its GHG, greenhouse gas factor, the total global warming potential is calculated and expressed in a common unit of CO2 equivalents. What if you were trying to decide if you should buy a window for your building from a company in New York or one in Arizona? Both suppliers provide the identical window, and the company in New York is closer to your construction site in New Jersey. But the one in Arizona is using on-site solar power to make its window, while the New York supplier is using its electric grid. The Arizona supplier is also shipping the windows in trains, while the New York supplier uses trucks. The Arizona supplier claims that the solar power and the trains make their windows environmentally preferable. The New York supplier says their windows are better because they are closer and their electrical grid is primarily coming from the hydroelectricity. Who is right? To learn more on what should be included in the LCA to answer this question, click the Modeling button. To see 3 possible results from this hypothetical example, click on each of the Results buttons. In order to answer the question, which supplier has the most environmentally preferable window, an LCA study would need to create 2 models, one for the value chain of each supplier, from cradle up to the point the windows are received in New Jersey. Starting with the window distribution, the New York model would include the life cycle inventory for shipping the windows 500 miles by truck. The Arizona model would include the life cycle inventory for shipping the windows 1,500 miles by train. For the manufacturing activity, the New York model would include the LCI data for hydroelectricity, while the Arizona model would include solar electricity. If there were any other differences in the manufacturing operations of the two suppliers, these would also be modeled and the LCI data collected. Let's assume there are none. Finally, the raw materials for each supplier would be modeled. Let's assume for simplicity that both suppliers buy their raw materials from the same companies, all located in Quebec, and that the New York supplier trucks these to its manufacturing facility in New York, and the Arizona supplier uses trains. These two different shipping models and distances would be reflected appropriately in the LCI data of each model. With the final life cycle inventory LCI data of each model, a comparative LCA for the two options can be calculated. To see possible results, click the three results buttons. In this example, we will compare two products. Let's say you are trying to decide if you should use vinyl windows or wood windows in your building. You've done your mapping, collected your inventory, and run your impact assessment analysis. These are your results. In some categories, wood is better, and in others, vinyl is better. Unlike the last example, this example shows trade-offs. No window is better in all impact categories, and you must decide which impact categories are more important to you. However, before you make a decision, it is critical to make sure that the comparison was fair. What if one window was triple paned and the gas filled and lasted 30 years, while the other was double paned, not gas filled, and only lasted 20 years? To assure a fair and transparent comparison, make sure your study has followed the International Organization for Standardization (ISO) LCA methodology. Click the wood and vinyl images to learn more about the trade-off. Typically, results of an LCA are displayed as either hotspot analyses or comparative analyses. If you're looking to examine more than one environmental or energy attribute of a product, a hotspot analysis can help you find areas where an investment in better alternatives makes sense. If you're comparing two or more alternatives and want to make sure you're not trading one problem for another, also known as greenwashing, a comparative analysis will support your decision-making. Read the on-screen text and click on the buttons to learn more about what an LCA can do for you. Click the resource icon above to download a copy of the International Council of Chemical Associations Executive Guide to deciding when it is time to commission a life cycle assessment. We hope that this short overview course on LCA has helped you understand what an LCA is, what it measures, and why you would want to commission one. If you are looking to examine more than one environmental or energy attribute of a product, if you need to examine trade-offs between design alternatives that could reduce the overall footprint of a product system, then it might make sense to consider the broad system approach that an LCA provides. If you do decide to commission a study, please sign up to take our 7 Key Concept course to help you efficiently manage your study and make sure you're following the ISO methodology.